Okay, guys, good morning. Happy Friday. Let's look at this real quick. Solubility. That one there, I've got it in color. This is a nice example of solubility. This compound here, we see this functional group, carboxylic acid. We don't know that functional group. It's got this amine, but more appropriately called what, since it's bonded to the ring?
Aniline.
Aniline. But it can be primary, secondary, tertiary. R groups. R is generic for carbon group. Okay. A lot of times R is defined somewhere where it needs to be defined somewhere. It's defined below here. And so really you have three different compounds. R being two methyls. It could be two methyls, two ethyls, or two propyls. Nomenclature video. Okay. If it's two methyls, it's called methyl red. These compounds are red when they're solids, but when they're dissolved, they tend to be more yellow. Okay? And here we have two solvents, cyclohexane, very nonpolar, and water. They don't mix. And so we can partition the compound between these two layers and see which part the compound goes into. If it's two methyls, it prefers the water layer. Why is that? That's kind of odd. That's a neutral organic molecule. Our opening statement was neutral organics come before organic. Well, that's kind of an exception. But it does have some polarity, including a good amount of hydrogen bonding potential with water. We see hydrogen bond donors, acceptors. We can imagine interacting with water. Okay. Still, it's a bit odd. Cyclohexane, very nonpolar. But look at this. If we change the R groups to ethyls and then partition it, more of the compound starts going into the organic layer. We can tell just from the color. Change these to propyl groups, and the compound highly prefers that. You would never be able to predict this, but relatively it makes sense because as we go from methyl to propyl, we're increasing the amount of just hydrocarbon. More hydrocarbon, more nonpolar. And the more it starts preferring the cyclohexane. Okay? Same thing down here, another application. Please read these types of things. They're meant to be applications, show the principle, see if you understand it, etc. I also give, this is also biological related, radio contrasting agents. Anybody familiar with these? Okay. But I want to show you that because I have the color one. So black and white. Okay, acid-base chemistry. Before that, though, we'll try with the lights off a little bit because it seems like the handouts are showing up better for some reason. That way. Lab this week, we'll meet downstairs at 2:30, see what type of questions you have. And then we'll go upstairs. We'll have to figure out which room, okay? Once you figure it out this week, then hopefully it'll be consistent going forward. Lab report for this lab is due when you come to lab next week, either Thursday or Friday. Okay. Next week you'll be doing unknown, determination of an unknown. It's actually a 2-week lab, but one of the things you'll need to do is a distillation. Okay, described in the pre-lab handout, but there's also a distillation video on the YouTube page. I think there's a lab demos page, and that's where you'll find the distillation demo video. All right? It's actually me demoing the distillation setup. So you're expected to watch that to be prepared for doing that. There's other demos there moving forward, but this one, distillation. Any last questions before we get started? Okay, acid-base chemistry, very important. We did our acid-base mechanism. How did we do on this warm-up question here? The acid-base mechanism will be used to show the products here. We use mechanisms to help us predict outcomes of reactions, as opposed to just like in math, you use formulas, right, to come up with answers. Do y'all use formulas? Okay, your mechanism is like that. You use your mechanism to come up with the outcome of the reaction, and then predict the product. We'll come back to that. Basically, when we do an acid-base, we need to identify the acid and the base. Those two react. The strongest acid and the strongest base within the molecule. The acid's pretty easy here. HCl is your acid, right? Thus, this molecule is going to have to act as what?
Base.
A base, thank you. Okay, but what? What's the most basic atom here? Okay, maybe you know, good. If not, sometimes it may be more challenging to determine other considerations. First off, you've got to have a lone pair, but several atoms have lone pairs. In the future, we may have to consider what's the strongest acid. Here it's easy. We need to understand how to identify the strongest base and the strongest acid. Because those are what will react. In determining the strongest, first off we're going to talk about acids. In determining the strongest acid, 4 primary things we look at. I assume you've read all this. Hugely important. I'm not going to read it to you. Okay? Our class time is super valuable. We need to cover stuff beyond just reading. Okay? Everybody understand this? Any questions about this table here? If you don't understand it today, then make sure you understand it after you move ahead. Okay, 4 things in determining strength of acids, which is more acidic, etc. They're listed here. We'll go through these 1 through 4, a lot like we did with the physical property intermolecular forces, or non-covalent interactions. We had 4 there as well. First one, electronegativity and size of the atom. I kind of group them together as one. We'll spell them out, separate them out here into 1A and 1B. 1A, electronegativity. Let's look at H2O versus HF. Which is more acidic? Which is more acidic? HF. Why? Under 1A. What's more electronegative? Fluoride? Okay. All right. Anytime we look at acid strength of acidity, we actually need to consider the stability of the conjugate bases. Conjugate base of water is hydroxide. Conjugate base of HF is F minus. Okay? You guys need to be able to show conjugate bases of any acid, right? All right. What we really need to look at here is which is more stable. Well, F minus is more stable. Why? Because it's more electronegative. Yes. Written right there. Okay? Everybody know electronegativity, periodic trends. F minus is more electronegative than oxygen. That means it likes being minus more. It's more stable being minus. That's what electronegativity means. It's more stable. Okay? Thus, it's more willing to form. HF is more willing to give up the proton and become the anion compared to water. Because when HF gives up the proton, it forms a nicely stable anion compared to what water would become. HF is more willing to do it. It's thus more acidic. More willing to give up proton equals more acidic. Which is more acidic, water or ammonia? Water? Why water? What we're really looking at here is hydroxide, right, versus what? Conjugate base of ammonia. NH2, 2 lone pairs, negative, right? Which is more stable? O minus or N minus? O minus, because it's more electronegative. Oxygen handles or likes being minus more. And when we say like, that's stable. It's more stable being minus. That's why it likes being minus. Or it can handle the minus charge rate. Thus, water is more likely to become the anion compared to ammonia. Ammonia doesn't want to give up an H plus and become the conjugate base compared to water. Water is more acidic. HF is more acidic than water. Which is more acidic, water or methane? H is on oxygen or H is on carbon? Which is going to act more as an acid? Well, this would be hydroxide, right? And what's the conjugate base of methane? CH3 what? CH3 is incomplete. CH3 what? And how many lone pairs? I predict about half you guys really need to, if I ask you to turn in on a piece of paper the conjugate base of methane, half of you would not get it right. You need to make sure you know what conjugate bases are. Okay? There's no exception. It's just as consistent as our acid-base mechanism. In fact, you can use the acid-base mechanism. We're talking about these serving as acids, right? Okay? There's some base. I'm just going to call it generic. I don't like using generic, but the base has a lone pair. If that's the acid, what happens? Here's our mechanism from the other page. This takes the H, right? What happens to these two electrons? They move on to the carbon as a lone pair. Okay? What do we then get? The base now has the H. Again, very generic, plus what? What did we form right here? CH, H, H. What's also on the carbon? Lone pair. It came from right here. Everything comes from the arrows. Right there. Moving on to carbon as a lone pair. Bam. But this has a charge. It's not a typical carbon. What's the charge? 1, 2, 3, 4, 5. Negative. There it is. That's the conjugate base. That's what you get after these species serves as an acid. Yes, water is more acidic than methane. How stable is a C minus? Is it very? Actually, it's not that stable because we're getting away from electronegativity. These guys over here tend to be more electronegative. Carbon is not considered that electronegative. It's sort of getting more towards the wrong side. We'll see carbanions, but they're not that stable, particularly compared to a hydroxide. Much more stable. Why? Electronegativity. Oxygen more electronegative than carbon. This is rare. CHs are rarely acidic because this is not that stable. It's going to have to be a good exception for a CH to ever have any acidity. Okay, that's electronegativity considerations. Size of the atom. Which is more acidic, HCl or HBr? What do we need to consider or evaluate? Stability of the conjugate bases, right? Okay, what's the conjugate base of these? Conjugate base of HCl is Cl minus. Conjugate base of HBr is Br minus. Which is more stable? Why Br? Cl is more electronegative. Yes, Br is actually more stable here. Because size of the atom trumps electronegativity when you're in the same group. When you're in the same group. Br is not as electronegative, but with Br, the electrons are more spread out because Br is bigger. The electrons are more diffuse. And that's the governing factor in determining stability. Size trumps electronegativity when you're in the same group. Okay, HBr is more acidic. Which is more acidic, HBr or HI? HI, because I minus is more stable than Br minus. Not because I is more electronegative, but because I is bigger. The electrons are more spread out. And so the negative charge, the anion, is more spread out. That's the overriding factor. For your hydrohalic acids, HI is the strongest. And HF is actually the weakest because even though F minus is the most electronegative, it's real small. What's the most acidic H in this compound? Most acidic H here? You got CHs, NHs, SH, and OH. Which is more acidic? The question is, where would you rather make an anion? Because when these serve as conjugate acids, they're going to become anions. Somebody again? SH? Okay, let's see how we did that. Well, let's compare this versus this. Would you rather have O minus or S minus? We'd rather have S minus because it's bigger and we're in the same group. Yeah. So that's going to be more acidic. Okay? How about this compared to this? Is it? That's a little hard to tell. Once you start going diagonal, sometimes it's hard to tell. But let's say, what if sulfur was here? It'd be larger. Sulfur being here means it's more electronegative than being here. If it was here, we'd say sulfur's the answer. Well, if it's there, then sulfur definitely is the answer, because moving over there makes it even more electronegative than if it was here. Or we could go back and look at this. We know this is more acidic than that. What about these two? Which is more acidic? Yes, that's more acidic than this, because when you're going across, electronegativity. Up and down in the same group size. Diagonal can be difficult sometimes. You'd rather have O minus. That's more acidic than here. But then, so we got rid of that, but then we can say between these two, that's more acidic because the S minus is bigger. So we can arrive that that's the most acidic hydrogen in the molecule. The SH. What functional group is that?
Thiol.
Thiol, yes. Or mercaptan, which is a little bit kind of odd. Thiol, yes. Okay, number 2 is inductive effects. Look at these two alcohols, and I've drawn it out in full Lewis structure. The difference is this one has a fluorine here. This alcohol versus this alcohol. Which alcohol is more acidic? Well, we want to consider the conjugate bases, right? I drew those over here, right? Conjugate bases. All right? The only difference is the F. Now, importantly, the charge is not on the F. So we're not talking about the size of the atom like that. And we'll clarify that maybe if we need to. What we have going on here is inductive effects by the fluorine. Fluorine is electronegative. Because of that, we have a dipole here and it pulls electrons. But the pulling here is felt through the entire molecule, although it sort of tails off. And so we can kind of call it like this. The fluorine's on the end there and it's pulling inductively. And when you pull through single bonds, that's called induction, or inductively. Now, question here. How do you stabilize an anion? Do you move electrons towards it, or do you pull electrons away? You stabilize an anion by pulling electrons away. Okay? And the pulling away is called induction through single bonds. Polarization. Okay? Here we go. I can pull electrons away from you by doing this. We're still bonded, but the electron cloud between us is more towards me. Okay? The inductive pulling pulls the electrons away from this anion, makes it more towards neutral, and leads to stabilization. This does not have that. There's your answer. This is more stable because of the inductive withdrawing of the fluorine group. Thus, this alcohol is more willing to give up the proton and become anion. By the way, we are talking about this H. Why are we not talking about the CHs? Because the OH is clearly more acidic, right? Based on above discussion. Now this guy has no fluorine pulling. It's sort of neutral, but one thing we can state is an sp3 carbon is actually electron donating by induction. Okay? You have to just know this because there's really no dipole here that's apparent. You have to know this. So we already really got the answer because this has the guy that pulls where this has nothing. This isn't very important moving forward. Okay? Let's look down here. Which is more acidic? This is methanol and this is ethanol. Has an extra carbon. Which is more acidic? The difference is an extra carbon, right? Okay? How does this carbon behave? What does it do in terms of its electronic? Sp3 carbon. It donates by induction. Okay? It donates. What's that going to do to the anion? Is that going to stabilize it or destabilize it? Destabilize it. Right? So which is more acidic? First one, right? Everybody good? Which is more acidic, ethanol or this branch called T-butanol? Don't worry about that. Which is more acidic? What do we got going on out here? It's hydrocarbon, nothing really. We do know that these carbons donate. Here we go. Whenever you have branching, it's like each branch donates. Donation, donation, donation. And this all adds up into a big donation into this carbon and into this area. So we're looking at the inductive donation of the sp3 carbons. Based on that, which one's more acidic? First one, yes. Everybody knows we're considering the anions, right? I just didn't draw them. You got an anion, and then you got all these, I call it like rich friends. They have lots of electrons they want to donate to you. Anybody got any rich friends that like to donate electrons? I got a lot of electrons here. Let me give you some. That's what these are doing. But the anion out here, right, is like, I don't need electrons. I got too many. So I'd rather just stay with my H compared to this guy. This guy doesn't have as much. So it's like, okay, I'll become minus. So because of a lot more inductive donation, this alcohol is less acidic. Now the difference is real small because they're both OHs. but we can predict that difference and say that this is less acidic. By the way, what's the approximate pKa of an alcohol? You need to get used to pKa's and start learning some. There's a list in the back of your lab manual. Approximate pKa of an alcohol? Approximate pKa of an alcohol? I can't hear. Somebody? 16? How'd you know that? Right here? And you understand why? Right? Alcohol is going to be more acidic than a hydrocarbon. Why? Because here the minus would be on oxygen, here the minus would have to be on carbon. Oxygen is more electronegative. It doesn't mind being minus, so it's more acidic, right? Hydrocarbon C minus is not that stable. It's not going to want to give up a proton to become an anion. Very low, high pKa, or low acidity, right? You need to understand that. Those are the trends we're trying to understand. Down below, which is more acidic? The alcohol with the F or the alcohol with the chlorine? Who says the one with the F? 3 people. Who says the one with the chlorine? Who did not vote? Okay. Who said F? Congratulations, you're correct. Yes, more acidic. Why? You guys that said chlorine, why'd you say chlorine? The chlorinated compound. Size of the atom only matters when the charge is on that atom. Is the charge going to be on this atom here? No, the charge is going to be on the oxygen. Which is bigger, oxygen or oxygen? The same, so that's not applicable. Size only matters when the charge is on the atom. What matters here? Inductive withdrawal. And even though the charge may be way over there, we're all bonded, and if I pull here, it's like tug of war. I'm going to affect you way over there. I'm pulling. Which pulls more, F or Cl? F. Induction is electronegativity. F pulls more. It's more electronegative. Okay? It pulls more. More electronegative. So this anion is going to be more stable. And so that original alcohol is more acidic. It's more willing to become the anion. Okay? How about down here? Which is more acidic, left or right? Now when you're doing tug of war, it doesn't matter how long the rope is. Any pulling here is going to affect way over there. In chemistry land, the effect of the electronegative atom does tail off and diminish as you get further away. Okay? So while you both got the same pulling to stabilize your anion, this is going to be a diminished effect. Because it's the more it gets away from the site of the anion, the less influence it has. Make sense? Or acceptable statement? Between these two, it'd be very difficult. Because you got a more electronegative atom, but it's further away. That's like comparing apples and oranges. I would never ask you that, because you have conflicting things. How do I deal with that? But these two, same electronegativity, but further away. Here we had different electronegativity, same position. Okay? So we want to make sure we're comparing apples, oranges, oranges. So that's inductive effects. Inductive effects are hugely important in organic chemistry as we move forward into reactions. Okay? The next effect we'll look at here is resonance effects. Resonance involves pi bonds, p orbitals. For your single bonds are sigma bonds, and hybrid orbitals. Okay? All right. Which is more acidic, this alcohol or this carboxylic acid? Hopefully you. It's called an acid because it's acidic. Okay. All right. Carboxylic acid is more acidic. Why? Well, we want to consider the conjugate bases, right? Since that's more acidic, that implies that this conjugate base is more stable than this one. This is more stable, so this is more willing to become the conjugate acid and give up the H plus to something. Why is this more stable? You could get the answer by just looking at induction or electronegativity. What's going on out here? Just sp3 carbons. What do? They donate. We just have to know that. That could be explained, but it's not ready to be explained. You got that donation, but what else do you have? You got this oxygen, and it pulls. Now it's not pulling directly away from here, but it's sort of like pulling, kind of away. Everybody agree with that? And that right there can give you the answer. That pulling, where this has no pulling, should stabilize this and make this more stable than that. And thus, that's more acidic than that. But the answer here is really resonance. Okay? Although induction may give you the answer is really resonance. Now, the resonance can be discussed in different parts, and depending how deep you want to go. Let's look at hybridization. These lone pairs are what type of orbital of this anion? Listen, all LPs are in what type of orbital? sp3, right? I don't know what, somebody said something, but I couldn't hear you. I reckon you said sp3, but if you want me to hear you and respond to you, you got to speak loud. They're all in sp3. Hopefully we know that. Okay? How about these lone pairs? What's the hybridization of the oxygen there?
sp2.
sp2. Okay. Why is it sp2?
Because the C is sp3, so it's got a pi bond for that oxygen.
Because the C is sp3?
Yeah. No, the C is sp2, and it's got a pi bond for the oxygen, which affects one of this lone pair.
Okay. The carbon's sp2. Carbon has a p orbital, so lone pair, the oxygen is going to want to be in a p orbital. Okay. We have an LP and a p orbital. And what's it doing in the p orbital? Is it interacting with the neighboring p orbital? Yes. Okay. And that right there is why it's more stable. Because here you just have 3 lone pairs, and they're just sitting there. They're doing nothing but just being lone pairs. And you actually have a third one as a result of it acting as an acid. It became a third lone pair, and it became an anion. At least one of these over here is doing something. It's interacting, okay, let's put it in a p orbital. And we got these pure, one electron. There's your pi bond. But we're going to put one of these, and we can maybe call it the extra one, the new one if you want. And it gets to interact as well, and that's a stabilizing effect. And that's called resonance. That's called conjugation. This oxygen is so-called resonance stabilized, where this oxygen is not resonance stabilized. So that's the stabilization going on here. It makes this more stable and that one more acidic. The idea of resonance we'll have to develop along the way, and guess what? We won't cover resonance until test 3. But by the time we cover it, it'll almost be partly reviewed. Now, a lot of instructors in textbooks cover resonance week 1 when we do Lewis structures. I think it's too much in week 1, and you don't get the full gist of it. You really need to understand it. So I do it a little bit along the way. As long as you're working there along the way, by the time we really officially are covered in, you'll be there. Okay? Why do we talk about the exception anytime a lone pair is next to a p orbital? Don't want to be in a p orbital? Because we're setting the foundation for resonance. Now, when you do resonance, you can draw resonance structures. Okay? One LP and a p orbital. We need to get used to drawing resonance structures. Definition of resonance structures was given before. This is just where you have this same connectivity, you just move electrons. But you only move pi electrons. Because as you think about it, if you move sigma electrons, you're going to be making a new compound. Only move pi electrons. And usually you move them according to dipoles considerations, electronegativity considerations. We have electronegativity here, right? This oxygen wants electrons. We can just move these pi electrons up onto the oxygen as the third lone pair and get this structure. But now we have charge. Now, on date 1 or 2, if we were trying to draw a structure, we would say, hey, we got to this point somehow, this carbon needs a bond. And so we probably took these electrons and moved them in, right? Said, hey, then you've got to share. Okay? And we went that way, and we said, hey, now we got a good carbon with an octet. Okay. But we can also consider going the other way, or coming back to maybe the original way. This has reasonable validity because oxygen is electronegative. Okay? I won't say any more. We'll build upon this. But from here, we could do another structure, though. Instead of moving these in to make double bond, what if we move these in and put double bond between this O and carbon? We could do that. Now, actually, these end up being same energy in terms of the best. These are the best structures, and they're equivalent almost. This one's not as good. We don't have an octet. We have 3 charges instead of 1, but it's still something valid to consider. This is more of the theoretical part of resonance. Now, anytime you can do resonance, the true structure is actually a blend of all of these. And if we blend these, we do that by looking at the number of bonds between the atoms. Here we have a double. Here we have a single and a single. What's the average of a double and a single and a single? Now, typically we don't do like an exact average, but it's somewhere between single and double. and we say it's sort of like 1.5. So between the C and this O is a bond and a half. This is supposed to be a half bond. That's a bond. That would be a double, but instead of a double, we're going to do a bond and a half. That's how much bonding is between there. But the same thing over here. Because it's got single bond character, but then some double bond character, and the average of that is somewhere in between single and double. So this is a 1.5. This becomes more of the true structure. What about charge? This option is negative, negative, but neutral. What's the average of negative and neutral? Somewhere in between the two. That would be partial negative. And the other option is also partial negative because negative, negative, and neutral. It's an average of all of that. And this is the true structure. We need to work at that, but here's hopefully a more easier question at this point. If this is the true structure, what's the charge on this oxygen here we're looking at? Is it full minus? It's partial minus. And that's a big consideration. This is called your hybrid. Any textbook you should be able to find hybrid, resonance hybrid. It's a partial minus. So here we can go back up here. Whenever you see this, you've got to see that that's a partial minus. Because there's resonance considerations. But that's a full minus. Because trust me and look at it. There's no resonance there. So which is more stable? Full minus or partial minus? Which is better? Partial minus is better. So there you go. That's another explanation of why this one's better. Okay? Go back to the beginning though, which was the short answer. One of the lone pairs here is in a p orbital. It's got something to do. And that interaction with the p orbital next door is a stabilizing effect, and that gives you your answer. That's not doing anything. Those lone pairs are just sitting there, not stabilized in any way. But we need to understand more the theory of resonance as we move forward. Please be reading. Okay. Resonance is when you have p orbitals interacting, and it leads to some semi-complicated considerations. Resonance is a very strong stabilizing effect, and it often outweighs other effects. Look at these two compounds. Which is more acidic? And I kind of gave you some information. Lower pKa, more acidic? Does that make sense? First off, what H are we talking about as being the most acidic? CH or NH? NH. Nitrogen more electronegative. CH rarely acidic. Okay? Talking about this. Again, your acidic hydrogens are often drawn in because they tend to be on your heteroatoms. If we didn't have pKa's, which would you say is more acidic? Or more? Would you rather have O minus or N minus? You'd rather have O minus because it's more electronegative. But then why is this more acidic? Because of resonance. Yes. Because boom, boom, boom. This would be, is any resonance going on there? That is one of the lone pairs going to want to be in a p orbital? No, there's no p orbital here. It's sp3. No p orbital. But look at this other one. Okay? You can just make it an anion if you want. How many lone pairs is the conjugate base going to have? Yes, 2. Negative, right? Okay? Because there's one here, right? The other one came from your acid-base mechanism. Okay? Are these lone pairs just sitting there doing nothing, or is one of them doing something? One of them's in a p orbital, right? Why? You've got p orbital next door. You also have p orbital next door here. It's interacting with that one and that one. And that interaction is a stabilizing effect for the lone pairs that are there. Sort of apples and oranges. Wait a minute, but this is more electronegative. But this has resonance. The example here is showing you that sometimes resonance can outweigh other effects. Right? It's kind of doubly resonance, that's why. If there was only one p orbital next door, it would not be as acidic as the alcohol. The alcohol would be more acidic, I just know that. Because it has two, it's like doubly stabilized. It's got extra overlap through here, and it makes it more acidic. Okay? So again, I have to go through this good speed, and then what I expect is next time you say, hey, I have a question about that last time. You know, I was looking at this, you know, on Saturday morning, I was watching Flintstone, and I was going over resonance, and I wrote down my questions here. Well, you know, let's answer one here, but the other ones, can you stop by office hours and we'll get your other 3 questions answered there? Or maybe after class. Okay? That's how we want to do. Because you're not going to learn everything right here, me going through it. You look at it ahead, you hear my description of everything, and then you follow up, right? Hybridization effects. Here I'm just showing you hydrocarbons, but we can look at any type of compound. Acidity. Here are the compounds. This H is more acidic than this H, and this H is more acidic than any of those. Well, the conjugate base would be on carbon, so we can't talk about difference in electronegativity or difference in size. They're all carbons. What can we talk about? Hybridization effect. If this acted as an acid, it would become this, right? I'll skip that one. I'll go over here to the other extreme. If one of these acted as an acid, such as that one, it would become this. Which is more stable? Well, this one is. Okay? Here's the answer. What type of orbital is this long pair in? What type of orbital is that in? It's an SP. What type of orbital is this in? sp3. There's your difference. Which lone pair is more stable? This one, why? %50 S. 25% S. And lone pair in such an orbital is going to be closer to the nucleus, right? More S character, more closer to the nucleus. The closer the lone pair is to the nucleus, the more stable it is. Nucleus is like mama. Closer the lone pair is to mama, the more stable the lone pair is. The nucleus is positive. The closer your charges are together, the charge separation takes energy. Okay? This is more stable because of what type of effect? Hybridization effect. That's your only argument you have here. But it's very important. Alkyne CHs have some acidity. It's going to be less acidic, even less acidic. Okay? Lone pair closer to the nucleus. Let's see where we're at. Okay. Next time we'll be starting with bases. Our bases will be the same considerations, but we'll just say that makes it, the opposite consequence. With bases, you want high electron density. Okay? It's the same considerations, we're just going to flip it over. We'll start there after our quiz on Monday. Quiz on Monday, mainly up the